Welcome to this lecture on the instrumentation for PET scanners. Here are the objectives for this talk. Recall that the basis of PET decay is imaging these annihilation photons. So even though the radiopharmaceutical that we're using is positron decay, it will annihilate within the patient's body, and the two 511 keV photons are emitted in opposite directions from each other, and that's actually what we're imaging. We want them to be considered a good count or a true count. We want these photons to be detected at exactly 80 degrees from each other at just about the same time. There are several positron-emitting radionuclides used in PET imaging: carbon-11, oxygen-15, nitrogen-13, and F-18 are all biologic materials. They are cyclotron-produced, and they have short half-lives, which limits their availability. Copper-64 is also cyclotron-produced, or it can be produced in a reactor, and that one has a slightly longer half-life. Rubidium-82 is generator produced, and that is primarily used for myocardial perfusion imaging, and gallium-68 is generator produced. Annihilation photons are the 511 keV photons that are emitted 180 degrees from each other in an annihilation reaction. The location of the annihilation differs at least slightly from the location of the positron emission, and this is a limitation for PET imaging that degrades the spatial resolution. So when we're imaging with PET, we're actually imaging coincidence imaging. This is where you detect the two photons in two different detectors within a short coincidence timing window. There are no collimators needed for this, but PET imaging does have electronic collimation. The process for coincidence imaging is that the light or scintillation photons are generated as the photon interacts with the crystal and is released from the crystal. Light then enters the photomultiplier tube or the silicone PM, the photodiode, and it's converted to an electrical pulse. SIPM means silicone photomultiplier, and this is one of the ways that digital PET imaging is performed. The electronic pulse then reaches the electronic circuits. As long as they reach it within a coincidence timing window, it's determined whether the event is true, random, or scatter. If it's accepted as true, then the count is placed on the sinogram based on the line of response. Sodium iodine thallium crystals that are traditionally used in gamma cameras are not recommended for PET imaging. They have a really low efficiency for 511 keV photons. The 511 keV photons tend to have enough energy that they pass right through the crystal without interacting with it. VGO has the highest detection efficiency, but it has a long decay time, so it has a low scintillation yield. Newer scintillators may have LSO, GSO, or LYSO detectors. These all have good detection efficiency, a high light yield, and short decay times. Time-of-flight PET cannot be done with VGO. So this is a summary of the comparison of the different detector materials or crystals that are used in PET imaging. I want to point out that sodium iodine thallium is on the list, but it has a long decay time. It has a really low density, and it's no longer used for any PET imaging. VGO is expensive. It has a low light output, a long decay time, and it is not supported with time-of-flight PET. You really don't see either one of those that much anymore unless you have a really, really old PET scanner. You might still have a BGO, but I doubt it. LSO or LYSO, these are more expensive. They have a high light output. They have a high density. Now, this density is important because that's what allows it to actually stop the photons and interact with it. It also has a very short light decay time. And so there have been some patent disputes with that one, but those do support time of flight PET and are still readily in use. The GSO is more expensive, has a high light output, somewhat lower than the LSO for density. It has a very short decay time, and this one is also no longer used. Down here at the bottom, it has the abbreviations for what they're actually made out of. BGO is bismuth germanate. LSO is lutetium oxyorthosilicate. LYSO is lutetium yttrium orthosilicate. And then the GSO is gadolinium orthosilicate. So those all have silicon in them for silica. And the GSO you might find in a really, really old scanner, but it's no longer used either. So the cameras that are mostly on the market today are either going to be LSO, LYSO, or they're going to be digital PET scanners. And this is a comparison of BGO to LSO. You can see why the LSO has replaced it. The image quality is much more improved with the LSO detectors. Time of flight PET is extremely important for understanding how we're able to image with PET. The scintillators with extremely fast decay times can be used to localize the point of annihilation reaction to a region of the line connecting the two crystals. This requires measurement of the time difference between the arrival of the two photons, and this requires very fast electronics as well as a fast scintillator. Essentially what happens is two photons will hit detectors opposite of each other. They need to hit within a picosecond time frame, and then as long as they hit within that time frame, it creates a line of response between the two, looks at the time difference between when those two photons arrive to figure out how off-center that photon originated from, or those two photons originated from, and that's how it's used to locate where it should be located on the sinogram. Basic design of a PET scanner, it will have many small detectors. They're arranged in multiple rings in a gantry through which the patient passes on the imaging table. A line of response is a term that represents how each event is detected by two detectors on opposite sides of the ring, and then they're traced back within a visible line to the event location somewhere along that line. Data is stored in a sinogram in which each pixel represents one line of response. This image illustrates how a sinogram is created and the projection concept of a sinogram. The set of parallel lines of responses constitutes a single horizontal line of the sinogram. And because you have photons being emitted in all different directions, the end result of that sinogram is that you do have diagonal lines that are kind of coming in every direction. And that's what's illustrated here in image C with the parallel lines of responses. There are four types of events in PET as the photons are hitting the detectors. A true event is what we want. That's where two annihilation photons from single annihilation interactions are detected within the coincidence timing window. This is, we call it a true event because it's truly what's happening that we want to see, where you have the annihilation reaction, it's hitting opposite detectors at the same time, and it's a true count. Next is singles, when only one of the two annihilation photons interacts in the detector. The other one may have gotten absorbed, deflected, or scattered in some way, and so only one annihilation photon interacted with the detector. Random are very difficult to filter out. That's singles from two separate annihilations that are detected within the coincidence timing window. It is extremely difficult to tell randoms from trues. And then scatter is two coincidences in which one photon was scattered before reaching the detector. So in that case, you do get two photons, but one of them was scattered before reaching the detector and ends up in a different position. And this diagram is showing the effect of increasing activity concentration on the count rates of trues, randoms, and singles. So as you increase the count rate, you end up getting more singles at randoms, but not necessarily more trues. So increasing the count rate doesn't really help you get more true counts. It also leads to more dead time and pulse pileup within the scanner. Attenuation is more of a problem in PET than it is in SPECT imaging due to the requirement that both annihilation photons be detected. It can be corrected for because the amount of attenuation does not depend on the location of the radiopharmaceutical within the object. And attenuation can be directly measured by using an external source of photons for transmission imaging if you have standalone PET, or if you have CT, then it's great to use the CT is actually the best method. This diagram is showing you how attenuation is corrected for using a transmission source. You have the rod source here, and the rod source will pass through the detector, or through the patient, I'm sorry, and reach the detector on the other side. And then you also have photon A and B, and so it uses that density and that attenuation, that loss from attenuation as the rod source hits the detector to determine the density of tissue and apply that to the line of response. Standard PET imaging reconstructs using a line of response as the potential location of an annihilation event. The time of flight PET uses the time differential between the arrival of the two photons as a measure of where along the line of response the annihilation event would be. And the formula for calculating that is essentially that the speed of light multiplied by the difference, time difference in the arrival times divided by 2 equals the shift in position for the location from the center of the line of response. And this represents the mathematics that are used for time of flight. In this figure, you see since the point of annihilation is on the right side of the object, photon A will be detected before photon B. Photon A is closer to the detector, so it will hit the detector first, and photon B has a little bit further to travel. So mathematically, we can determine the timing difference between the arrival of photon A and photon B. And the timing electronics do not allow for the time change to be known exactly, but even the ability to localize the annihilation event to a portion of the line of response improves the signal to noise ratio and spatial resolution and overall quality of the image. PET also has an ability to provide quantitatively meaningful results, and that's one of its greatest attributes. This allows for measurement of physiologic quantities in real life. It's used for new drug development, even for treatment efficacy, and it determines the attenuation and scatter correction, as well as determination of a calibration factor that correlates count density with activity concentration. This is an overview of the tomographic composition. Scintillation crystals are rectangular prisms that are about 4 to 6 millimeters square, and they're 20 to 30 millimeters long with a long axis oriented in the radial direction. There are 18 to 32 rings of those detectors in a gantry. However, many rings are in the detector is very manufacturer and model specific. Some of the newer cameras actually have more than that. And then there's a gantry bore through which the patient and the imaging table must pass, and that is typically about 50 to 60 centimeters. The axial field of view is the length of the gantry bore in the axial direction, and that is typically about 15 to 18 centimeters. Transaxial field of view is determined by the detectors that are allowed to be in coincidence. Detectors are grouped into detector blocks. Two annihilation photons must be detected within the coincidence timing window and in two blocks allowed to be in coincidence. If coincidence is determined, the two individual detectors registering the event are identified and the line of response between them is determined. And older scanners, with the time of flight in coincidence detection window is precise down to about 5 to 12 nanoseconds. Some of the newer ones are much faster than that. And coincidence is added to 1 pixel of the sinogram once it's determined that a true count has been detected. Many studies require multiple acquisitions to include the entire area of interest. Each location of the imaging table is called a bed position, and an acquisition is done at each bed position. Bed positions are then added together to complete the entire 3D image matrix. A typical FDG oncology study is from the base of the brain to mid-thigh, or from vertex to mid-thigh, sometimes vertex to toes. And typically, though, it's base of the brain to mid-thigh, or eyes to thighs, or skulls to thighs, as it's sometimes referred to. And that could be anywhere from 5 to 6 bed positions based on the patient's height. For cardiac and neurology dedicated imaging, typically those studies only require 1 bed position. Events can be detected in direct planes or cross planes where two scintillation crystals are in different rings. The histogram mode is equivalent to frame mode in single photon imaging, and this is set up the histogram matrices ahead of time and then add events as the acquisition takes place. List mode acquisition can also be used. List mode acquisition is very common with cardiac PET imaging. The PET scanner will acquire 2 to 3 sinograms for each direct plane and for each allowed cross plane. A prompt sinogram is essentially the raw data. This is all the events that were detected within the coincidence timing window, and this is comprised of trues, randoms, and scatters. A delay sinogram provides a measure of random coincidences, and the transmission sinogram is only seen in PET-only systems. If you have a PET CT, you do not get this, but the transmission sinogram is from the transmission scanning portion. This is an example of the emission volume and detectors versus the sinogram. So as you can see, wherever there is counts that occur, then you will have photons hitting opposite of each other. That creates that line of response, and then that line of response is added to the sinogram, and it will show you exactly where that is located along the sinogram. So this video is showing you how those lines of response between the PET detectors and the corresponding location on the sinogram. It's essentially just a map laid flat where each one of these rows on the sinogram is a different layer or different line of response that was acquired. I also want to point out, as it looks like these different lines of responses are kind of moving around the patient, this is not x-rays coming from the machine or anything like that. These are the photons that are coming from the patient and hitting detectors opposite of it. Of course, that all happens simultaneously with the PET scanner, but for visual purposes, it's showing you how each of these different angles, each of these different layers is um, creating that location on the sinogram. So a typical detector block is a set of 36 to 64 crystals. Remember, those crystals are very small, and then they're coupled to 4 PM tubes. The scintillation light pattern is different for each crystal within the block. Once an event is determined to be in coincidence with another event, the Anger positioning logic or lookup table are used to identify the specific crystal that was detected. So this is a diagram of a detector block. These scintillation crystals are about that size, and you'll have kind of rows and columns of them that are each about a millimeter by a millimeter or so, and then they're coupled to 4 PM tubes. So this is an example of a detector block. I believe that's one from a GE scanner, but you see these millimeter by a couple millimeter. These are the crystals. They are directly coupled to the PM tube. There's 4 of them here, and then that makes up one detector block. You see it from another angle over here on the right, and this actually shows you, you can kind of see the diodes, and then you see the preamp and the amplifier connected to the back of the PM tube with all the circuitry. And this is showing you in the bottom in diagram B, it's showing you the differences between true, scattered, random, and multiple or single. You have single events that can occur there also. So a true event is really what we want. That's where you have that positron emission that annihilated in the patient's body, very close to the source, and then the 2 photons hit the detectors opposite of it within the window and can be counted. Scattered is when one of them scatters and they still hit detectors opposite enough of each other that a line of response is created. This will lead to misplaced counts, so it greatly does impact the background and the image quality. Random events are when 2 annihilation photons that are completely unrelated just happen to hit detectors opposite of each other. A line of response will be created. This also contributes to background and degrades the image quality. And you notice that it's placing counts where there really shouldn't be counts. Singles are, of course, let's say in the scattered event, 1 photon hits the detector, but the other never does. That would be an example of a single event. And then when you have multiple events, that's where you have multiple events hitting within a coincidence timing window. And the scanner can struggle to create accurate lines of response with that sometimes. So you end up getting more randoms that way. And this image here is showing you what the digital detectors look like. This is an example of one with an LYSO crystal, and then you have the 8x8 silicone photo multiplier, basically a photodiode there that's coupled directly to it, and then it's got the adapter board, and it's all electronics from there. So this is a much smoother, much smaller system than the full detector blocks. And this is what the digital PET detectors will look like. These are some more examples from some other providers or other manufacturers. I want to point out that with these digital detectors, this is 26 by 26 millimeters, but just the square that's listed here is 16 detectors in it. So much very detailed small components for the positioning logic, and the ability to actually place counts where they need to be. You'll notice that each one of these has other smaller arrays within it. You have a 4x4, and so you have the optical crystal with pixels in it. That's a pixelated system. And then you have the SIPM tile that's attached right to it, and then the analog digital converter and processing information from there. It's all electronic. So it's a much more compact system, and it's mostly electronics that allow for that digital image. Taking the PM tubes out of the system does increase the sensitivity and the spatial resolution. There's a lot of problems that can occur from the PM tubes, and the high voltage supply, stabilization to those, and so forth. This is a much more efficient system. Now, the pulse height analyzers are used to determine photon energy and eliminate the scatter events. The choice of energy window determines the scatter fraction and therefore the degree of scatter correction that's needed. It's pretty typical with PET to have a wide window of about 35% or more, and the effective energy resolution is 10 to 25% in commercial PET. That does increase a lot and improve when you have the digital PET or the solid state detectors. A delayed sinogram has a hold. It will hold each event for several coincidence timing windows and then regenerate the signal. If an event is detected in the same line response but a delayed window, it's added to the delay sinogram. And this also helps for an estimation of singles. That's the measure of single rates at each detector. This is a mathematical estimate of the likelihood of two singles being detected by any two detectors. Positron emission attenuation is in the transmissions is done with transmission scanning if you don't have CT. That's done by using rod sources of germanium-68, which decays to gallium. A single photon attenuation nuclide like cesium-137 pin source, or if you have a CT system, you can use a CT generated attenuation map and apply that to the PET tomograph. The application of a CT attenuation map is the best method for attenuation correction. This is how the transmission sources from standalone PET will acquire. The transmission source configurations could be one single photon source with shielding or a positron emitting source that's in the shape of a rod. So they effectively eliminates the acceptable events to a narrow beam geometry when you have the rod source. If a single photon source such as cesium is used, a broad beam situation is encountered, so the difference is measured linear attenuation coefficients is larger than would be expected from the energy difference alone, and the cesium must be shielded from the nearby detectors in order to do that. All of the following corrections get applied to the line of response. Normalization corrects for variability in the detection efficiency between the detectors. The dead time corrections corrects the measured count rate to the estimated and actual count rate. Scatter correction, attenuation correction, and then decay correction. Decay correction is used in studies with multiple bed positions or dynamic studies, and this has to do with the short half-life of the PET radionuclides. And this is showing the effects of normalization correction. The top rows show reconstructed transverse slices, and the bottom row, the sinograms. The leftmost set are uniform cylindrical phantom, reconstructed without application of normalization. The middle set is the same acquisition but corrected. And then the one on the right is the difference between the two. So you see that it really is important to apply those correction factors. Scatter correction is done by using a count profile through a cylindrical phantom. Scatter is estimated from the remaining counts in the tails of the count profile beyond the boundaries of the phantom. That technique is used to estimate the scatter in 2D PET. Now 2D versus 3D, the image over there on the right shows the difference in the count rate between the two. With 3D imaging, it retracts the septa and allows many more events to be registered. It basically allows for some of those ones that are not directly 180 degrees from each other to be counted. You get more randoms and scatter with 3D imaging, but you also have increased sensitivity. With 2D imaging, you have less overall sensitivity, but the counts that you do get are better quality. You don't have as many randoms and scatters, but the 2D imaging will incorporate a tungsten septa between the rings of crystals. They absorb the cross-plane annihilation photons and improve the image quality, and they also decrease the number of scatters and randoms. So 2D can include or exclude a limited number of cross planes. 3D can use all possible cross planes or eliminate the most extreme angles. Each acquisition choice determines its own set of corrections, scatter models, and reconstructive considerations. Filtered back projection was used in early PET image reconstruction, but this leads to a significant noise and streak artifacts even outside of the patient's body. Nowadays, iterative reconstruction is used, especially when you have PET-CT, and OSEM is the most common reconstruction method. That stands for Ordered Subset Expectation Maximization. This uses select subsets from each data to reconstruct with less iterations. Example, there may be 80 to 30 subsets, but the data undergoes 2 to 4 iterations. So this is much more efficient, and other reconstruction methods like MLEM require 20 to 30 iterations of the entire data set. So more and more you'll see OSEM even for some of the dedicated SPECT or multi-pinhole or solid state systems with SPECT, but especially with PET, you'll see more and more OSEM. Some other choices when acquiring PET images. Images can be dynamic and gated. This is usually in a single bed position. One of the tests that we do often that we would use dynamic or gated for would be cardiac PET. Time of flight PET tomograph. For this one, you want to use a lutetium-based scintillator, and then the data is stored in list mode. And there are organ-specific systems out there, such as the dedicated breast imaging for PET mammography and dedicated cardiac PET imaging. So some of the image characteristics with PET, background is always going to be a problem. You have incorrectly positioned events that do become part of the background, especially from those randoms and scatters. Noise, you want to consider this on a line of response by line of response basis. Dead time is a problem with PET. Singles must be held to verify the lack of coincidence. This also happens with randoms and multiples. With singles, it not only holds the coincidence timing window, but it holds each detector opposite of each other until it can determine if it's a true count or not. Patient motion is also a problem in PET. If you're doing cardiac imaging and you have motion, that can really affect the quantitative data, especially if you're doing myocardial blood flow or you're looking at fused images on PET-CT. And then for the brain, that motion can kind of misplace the brain with the images. And respiratory motion always seems to be a problem for cardiac and oncologic imaging. There are a lot of sources of background in PET imaging. There's a non-specific distribution of the radiopharmaceutical. Just because of the nature of positron emission, that positron particle is going to travel in the body a little bit before it annihilates. So you have a little bit of non-specific distribution of the radiopharmaceutical, and the whole physics of that can contribute to background. Random and scatter events will both contribute to background, and there are inaccuracies based on the line of response and the reconstruction methods. This is greatly improved with time of flight technology, but it remains a problem with PET imaging. Noise is also a huge problem with PET imaging, and it is much more difficult to fix with PET than it is in regular nuclear medicine or SPECT. It is caused by variables in the radioactive decay, the reconstruction process, the random and scatter events, and attenuation. There are some corrections that may actually increase noise, and there are uncertainties within each voxel due to the line of response. Random coincidences occur from everywhere, and iterative reconstruction is often preferred because it's better at filtering noise than the filtered back projection is. Dead time is also an issue with PET. Mostly it's caused by single events. Remember that when a single event hits in a detector within the coincidence timing window, it will not only cause dead time in that detector, but the one opposite of it, as it's waiting for the other opposite coincidence photon to hit the detector opposite of it. When that never happens, essentially what happened was both of those detectors opposite each other experienced dead time when no count was counted. There are also multiple coincidences that can lead to dead time, and the detectors are unavailable to accept new events while they're processing. This is magnified by the detector block designs that share a PM tube. Patient motion will create blurring. Attenuation correction often makes motion worse. This results in over and under corrections that create photopenic areas and hotspots. Artifacts can be identified by reviewing the data for artifacts before sending it to the doctors. Attenuation and scatter. Non-attenuation corrected images look very different from attenuation corrected images. Scatter must be subtracted before the attenuation correction, and then subtracting that scatter increases the noise, but it decreases the total counts. Verify hotspots by looking at the non-attenuation corrected images. If they are present on the non-attenuation corrected images, then it's a true hotspot. If it is not on the non-attenuated and it's only showing up on the processed images or the fused images, then you know that that's actually a artifact that's caused by that attenuation. This is an example of a patient with out attenuation correction with, and then the CT. You'll notice that there's some hotspots here, and they actually got a little bit more normalized and corrected for once the attenuation was applied. You also see a cold defect here, cold spot defect, and that's because the bladder was so hot. That gets corrected with the attenuation correction. And some of the hot spots that you see up here were actually corrected for as well. The voxel size with PET depends on the system's field of view and image matrix. If a 128 by 128 matrix is used with the 50 centimeter field of view, then you will get 4 millimeter pixel sizes. 256 by 256 with 50 centimeter will result in 2 millimeter pixel sizes. Most exams are going to be 128 by 128 matrix. Brains, though, are best with a 2 millimeter pixel. That's going to give you slightly different, slightly improved spatial resolution. And the pixel size should be less than half the full width half max. There's a partial volume effect that can occur where counts will spill over into the neighboring voxels. Now, with the partial volume effect, counts from a small volume are spread out over a large volume in a reconstructed image. Essentially, the pixels become kind of saturated and they spill over into the neighboring pixels. Think of it like a bucket that's filling up with water, and eventually it may fill up and overflow and spill into the neighboring buckets. That's kind of how, that's kind of a good analogy there. But measured activity concentration is less than the actual concentration per pixel. So essentially, it just takes a really fine point of high activity and it spreads it over several pixels. So each pixel is less intense than it would be if it were just showing the one, but it's kind of spread those counts out over several pixels. For quantitative purposes, a correct partial volume effect, you can correct for partial volume effect by multiplying the observed activity concentration in a small lesion by the recovery coefficient. Image contrast is a result of background, noise, dead time, attenuation, correction, or attenuation, scatter, and motion. And contrast is most improved by lessening the dead time and having accurately determined corrections, especially for randoms and scatter. Contrast is degraded by patient motion, elevated background, and systematic or random errors in the correction matrices. So very important that those corrections and calibrations are done in time with your QC, and that is all kept up to date, because those calibrations and corrections get applied to every patient image. If they're allowing too much background, too much scatter, too many randoms, anything like that that's not accurately being applied, then it can degrade the contrast and the image quality. Spatial resolution depends on a lot of things with PET. The choice of the radionuclide. With PET, the positron, the effective positron range, or how far that positron will travel, has a lot of impact on the spatial resolution of the scanner. And some positrons have a lower energy and they won't travel as far before they annihilate. Those radiopharmaceuticals with lower energy that don't travel as far will have better spatial resolution. Positrons with higher energy tend to travel further and they have a longer effective positron range, and those will degrade the spatial resolution. The size of the scintillation crystals influences the spatial resolution. You can only detect as small as those scintillation crystals are. And then location in the gantry, you have better spatial resolution at the center of the gantry than you do at the outer part of the patient bore. And the line of response is dependent on detector size. Newer models will have smaller detectors. Sensitivity depends on the choice of scintillator, the detector geometry, the choice of the acquisition mode, and the correctness of the applied corrections, such as like random and scatter and things like that. 3D mode is more sensitive. You'll get a higher count rate. So 3D mode will have better sensitivity, but it will oftentimes have less spatial resolution and worse contrast. So it depends on what you're actually trying to image there, but it's really careful to make those. You'll need to be really careful to make those choices and follow the manufacturer's recommendations when you're doing something new, like brain imaging or something that requires a lot of spatial resolution. The scatter fraction is the ratio of a scatter coincidences to total counts after the subtraction of randoms. This depends on the design of the tomograph, the presence or the absence of the septa in the electronic collimation, the energy window setting, and you can estimate this using the cold spheres phantom. The spheres should be at least 3 times the full width half mass. The noise equivalent count rate is the most appropriate quantitative expression of count rate, and it allows us to compare scanners that way. The formula for that is listed there on the screen, and you can operate your tomograph at or below the peak noise equivalent count rate. These are showing the components of the noise equivalent count rate. This expresses the count rate in a PET acquisition in a way that it takes into account for the random and scatter rates. It's recommended that the tomograph be operated at or below the activity concentration corresponding to the peak. There are quite a few inherent limits on resolution. The resolution variation of the radionuclide used, non-collinearities of the annihilation photons, the ring geometry. There's a variable density in the lines of responses, the depth of interaction or the parallax. Photons cross from one crystal to the next, and then decreased sensitivity due to small active area that's actually receiving the annihilation photons. There is an interplay between the administrative activity, the dead time, and the noise equivalent count rate. Dead time in PET is primarily related to the singles. Random and scatter coincidences cause image degradation. They will decrease the image contrast and increase the noise in the background. And then noise equivalent count rate does not peak at clinical dosages in 2D mode. In 3D mode, the maximum noise equivalent count ratio represents the optimum counting rate for a particular tomograph. With 2D mode, the scatter fraction and the dead time are low. The noise equivalent count rate shows a slow increase with activity concentration, and the spatial resolution is improved. With 3D mode, your greatly increased count rate, it also increases dead time and scatter fraction, and you have more variation in both sensitivity and spatial resolution. Time of flight acquisition does help to gain clarity by limiting the location of the annihilation to a small part of the line of response. There is a difference in arrival times of the two photons, and that's related to their distance from the center of the x-axis. Uncertainty exists in the determination of that difference of location in the x-axis, and that's related to uncertainty in the timing measurement. Time of flight, though, is very beneficial to PET, and the chief benefit of time of flight is the improvement in the signal to noise ratio by a factor of 2 to 10. So it will greatly decrease noise and increase the true hotspots that you see in an image. Standard uptake value is a quantitative measure. And you see that this one is automatically calculating the SUV value. It's drawing that region around the hottest pixels, and then it's using that to calculate the SUV and the SUV maps, which are listed down here. So SUV is a quantitative measurement, and quantitative PET relies on well counter calibration between the tomograph and the dose calibrators and the well counters to measure the activity values. Units of counts per second per voxel divided by becquerels per milliliter and the value depends on dead time, noise, and scatter. Different calibration values are required for different acquisition modes. This is a calculation for the standardized uptake value. And like I said, this is a semi-quantitative indicator of tissue uptake. The SUV equals megabecquerels per milliliter in the area of interest divided by the injected dose divided by the patient weight. So this depends on the expression used for body weight, how tissue concentration is determined, and whether to apply the partial volume correction. SUV is a quantitative measure of the magnitude of radiopharmaceutical uptake within a certain area. Value of 1 indicates a complete even biodistribution. An area of increased activity will be greater than 1. It has been used as a cutoff value for looking at malignancies in FDG, but you can expect a 10 to 20% variability between sites and a 10 to 15% variability at a single site. SUV is still becoming more and more of a common measurement. Factors that affect SUV will vary from one radiopharmaceutical to the next. And one of the effective positron range influences that as well, because that's our scanner's ability to really see where that was locating, where it was coming from. And it will degrade the spatial resolution, which can degrade the SUV values. Factors that are affecting the SUV for FDG include blood sugar at the time of injection, time between injection and imaging, and uptake into other tissues like the myocardium or brown fat. SUV is sometimes used as a biomarker. It's quantified uptake of a PET radiopharmaceutical, and it can be used as a marker for new drugs. It allows for quicker determination of therapeutic effect compared to clinical endpoints. It requires a great deal of standardization within and between research institutions, and the SNMMI Clinical Trials Network certifies institutions to participate in these biomarker studies. This is a review of the overall process of PET imaging. You have radiation over here that's hitting the PET arrays. From there, it's going through the amplification process and digital to analog converter. And it goes through the timing control window. And I want to point out too, the DAC has to do with the power supply that it supplies to the PM tube or the detector arrays. And then you also have power management. You have the UPS that helps with that as well. And that's important. There's a clock source that helps with the timing and control, or the coincidence timing window. And it is important for that to be synced. That helps not only with the coincidence timing window, but also for decay corrections that it makes. So in summary, there are a lot of factors that play into the image appearance in PET. These factors may change depending on the tomographic system design, choice of acquisition modes, the radiopharmaceutical that's being used for imaging, and lastly, standardized uptake values are the chief benefit for PET and are becoming more and more important in drug research and even in oncology. And that concludes this lecture. I hope you enjoyed it. Thank you for watching.